Thank you for joining to watch my video regarding Fabry Pérot interferometers on our course on laser physics. So, what I will be describing to you during this lecture is that first I will be starting with a brief motivation, why we are interested in Fabry Pérot interferometers or étalons or Fabry Pérot resonators in general, and then I will be going through very briefly a derivation, how do we extract the useful parameters describing a behavior of a Fabry Pérot interferometer. So essentially we will be going through how we can calculate and how we can operate on transmission function. So basically that would be a function telling us how light, different colors of light will be propagating through this kind of Fabry Pérot interferometer. Then we will be speaking about free spectral range, which is another important and useful property to understand how these interferometers work. And then finally we will be talking about the cavity finesse in our description. So this is what we will be talking about, and then I will be just straight away start by briefing out with the motivation. So Fabry Pérot interferometers or resonators is essentially the same thing. They basically are optical cavities or resonators, using different word here, and they are formed by two planar partially reflecting mirrors, are placed parallel with each other. So that's the kind of configuration we are dealing with. So this is the kind of simplest possible cavity configuration we can imagine and think of when we are building optical resonators. The formed Fabry Pérot cavity or resonator, it's resonant at specific wavelengths. And what happens is that at these specific wavelengths, light is being trapped inside the resonator mirrors. And in a way, you can understand that the light just bounces back and forth multiple times between the two mirrors that are highly reflecting in nature. These kind of components are used basically everywhere if you think about it more carefully. So they are really being used in numerous photonic applications, ranging really from short laser cavities. So for example, these vertical cavity surface emitting lasers, VCSELs, and I'm sorry about me podging this acronym in the previous lecture. So of course, this is not anything about the kind of vertical cavity semiconductor blah 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 lasers, but rather vertical cavity surface emitting lasers. Then these Fabry Pérot interferometers can be used to make spectral frequency filters. So basically, those would be the étalons, sometimes put inside laser cavities to restrict the lasing into unwanted modes. For example, you can make a single longitudinal laser using a smartly placed étalon, but more on that in the later chapter description when we are really building or thinking how we are building a laser. And of course, finally, we can imagine that we could use these kind of devices for spectral analysis applications in general. So basically, light only at specific wavelengths is being transmitted or reflected. So if you would happen to know what that color of light actually is, then we could use these for spectral analysis. So these are basically just a few of the application areas that we can find for Fabry Pérot cavities. And now we get into the actual mathematical business of deriving things. And since we already have covered multiple beam amplitude splitting interferometer behavior in our previous course, we have also covered the derivation of the math, how do we understand how a Fabry Pérot interferometer works, in a previous lectures in our optics course. So basically chapter 8 on interference. The lectures are openly available in YouTube, so if you're really interested in seeing the derivation, please check out the videos behind that QR code, and you are able to see the full derivation in all its glory. But here, we do not really need to be dealing with the full derivation. It's enough that we just go through the main results, and there we start by considering the reflection and transmission at the interface, and just noting that if you don't have any losses due to scattering or absorption, then basically the reflectivity is squared and the transmittivity is squared. The modulus of these values equals to unity. So this physically basically just means that we are considering a lossless system. So we are basically conserving energy. So I guess I could hand wave here. What happens is that basically all light either gets reflected or transmitted, but there's, for example, no absorption within the material. And we are also assuming ideally flat surfaces so that there's no kind of like erroneous scattering taking place here. That would also be seen as a loss mechanism. So basically these are the assumptions we are making here. And of course in real life we all know that there is no such materials that are not lossy, and there are not materials that are ideally smooth either. So of course in real devices this approximation would fail epically. But in kind of like going through the math on this level, I think it's a good approximation and assumption to make. So let's go with that. So the system has been studied during our earlier course, like I already mentioned, and here we only go through the main results. And we are here first interested in calculating or outlining how does the transmission look like for this interferometer. So we have an input field. So the input field basically is of this form. We assume that it's a plane wave. So we have a given amplitude E0, and then we have a planar wavefront hitting the interface at a given angle. And then we are interested in calculating the output, and the output basically is noted as a T as in transmitted field, and basically that's a summation of all the subfields that are being transmitted through the interface. So basically physically what happens is that we have an input field. Part of that is being reflected, but part of that starts becoming like a partially reflecting and transmitting field here. And then we are interested in looking at the transmission function, so how much of light actually gets through. So we are interested in calculating the sum of these fields of different contributions. So basically the total transmitted field, the output field of interest here, is basically the sum of all these subfields here. And if you're really interested in the derivation, please have a look in the previous lectures on a previous course. So we really need to only just look at the first two terms to get an idea how the transmission function looks like. So we just look into those contributions now. So that the first transmitted field contribution is basically a multiplication of these two different transmission functions. So here the prime notation just means that we are going through from the obliquely dense medium. So from the kind of like a thin membrane or etallon, we are going into air. So that's the transmission function towards that direction. And here we have the transmittivity for the interface coming from air into the optically dense material. And this was the amplitude of our incident pump field. Here, phi is basically the propagation phase from point A to point B. Please look at the previous figure. So that's basically from the top surface into the below surface and how the phase accumulates there. We do not really need to consider what is the actual form of this phase function. So I will not outline the actual functional form for this one. It's just enough to know that it's there, it exists. But if we are finally looking at the irradiances, we do not really need to be here caring much about the actual field. Then we look at the second contribution into the total transmitted field, so E to T. So that's basically then like 2 times reflections happen. So we have R prime squared, and again we have the previous term as in the previous case. And then here we have an additional phase term arising from the fact that we are having a propagation of field from the point like basically B at the location of the first interface where we are like having the ET1 emitted. So this phase term basically comes from the phase difference, that how much of phase of this field contribution is being changed with respect to this field contribution when they are finally propagating at the same wavefront. But again, if you're really interested in seeing how this form looks like, please look at the previous lectures. It's slightly non-trivial because you do need to calculate the whole phase evolution of both field contributions. So it's not exactly clear by just looking at the figure for 1 or 2 seconds, but you actually need to calculate things. But in any case, how it looks like is that it looks something like this. So we have 2 times K times NT times D, that's the thickness of the etallon, times cosine theta T. So that's the angle at which the ray makes within the optical material. And we can see here that a repeating factor actually is taking place within these subfields, and that's given by R prime squared times exponent I delta. And this then gives us possibility of calculating the total transmitted field, which becomes ET equals TT prime times E naught times exponent EI phi, and then we have these kind of terms. So 1 plus R prime squared exponent I delta plus other terms. And basically we can now write this in a different form by taking use of a geometric series. So basically this guy here can be written using geometric series, and that simplifies the mathematical description. And then we can equate that this t times t prime actually equals to 1 minus r squared, as long as we are conserving energy in the system, and that was the implicit assumption we made. And then the same thing here, we can replace this r prime squared with a just r squared term. So that's the final conclusion that we get for the transmitted field. And we have taken use of the geometric series, basically of this form, that can be used to basically approximate this kind of form into this form. Now, okay, so we have now basically a transmission coefficient, and that operates on irradiances rather than fields. So basically we can now calculate that, and we can commonly define that transmittivity or transmission coefficient as a modulo square of these two different field contributions squared. So now we basically have the input field given form. That was the assumption we made, and now we have calculated the output field, and now we can just calculate the whole transmission coefficient using those. And what we get out is looking something like this. So basically we have replaced the small r squares with capital R. That would be the kind of a reflection coefficient operating on the irradiances, and then we have this kind of a phase term here arising from the actual thickness and optical path length differences for the different contributions. So this we can really define or call that let's call this as a Airy function, and that can be used to simplify the kind of writing of our mathematics. And this is basically the transmissivity of our Fabry-Pérot interferometer. And this, like I already said, is also known as the Airy function. And let's now just remind us what were the assumptions we have made to get this far. So basically we assume that the reflectivities or reflection coefficients, small r's, r and r prime, they are equal, and that gives us a tool to calculate the reflection coefficient. So capital R, so that's essentially r modulo squared or r prime modulo squared. And then we have this phase factor, so delta times phi, so that's basically given the previous course's notation of 2 pi phi nu divided by speed of light times capital lambda, where this capital lambda is basically the kind of phase difference between subsequent subfields, so of this form, and this gives rise to a wavelength or frequency dependent transmissivity. In other words, the fact that this transmissivity really depends on the frequency of light. So basically we are interested in this, and we see that here we actually do have a phase dependence that depends on the frequency of light by looking at this equation here. So that's the way how do we calculate the transmission coefficient that operates on the irradiances, and that's nice. So we can now calculate that for a given variables and parameters for a given system, we can now calculate how does the Fabry-Pérot interferometer actually behave. And now we get forward, so now we will be outlining to you how the so-called free spectral range is calculated and how does it look like in our case. So the Airy function t is a periodic function. So really how it looks graphically or physically, basically it's a series of pulses, and the period of these pulses, so that's basically the delta nu FSR free spectral range given by speed of light c divided by 2 times n. That's the refractive index of that material times L. That's basically the kind of a d times cosine of theta. So what's the kind of optical length of our Fabry-Pérot interferometer? So L is basically the cavity length. So this variable delta nu FSR is known as the free spectral range. And basically what it physically tells us is that it tells us the kind of separation between the subsequent pulses. So this is basically how a single area function gives out, what kind of like peak we are getting out, and then the free spectral range, how far apart these subsequent peaks are. And this is actually extremely important when we are like making components based on Fabry-Pérot interferometers, and then we are placing those within cavities. The free spectral range basically can be described directly by that sine squared term, because that's the term that gives rise to the periodic nature for the transmission coefficient T. So that's where it comes from. And now we will speak about a little bit about finesse. So that's a final kind of thing we want to be outlining to you during this lecture. So now we will be looking at the transmission peaks, and we will be looking essentially how sharp these peaks are, and essentially how sharp these peaks are with respect then finally to the free spectral range. So in a way, this finesse tells something about the quality of the resonator in question. Usually higher finesse resonators in some applications are extremely beneficial to be able to use. So in a way, this is a kind of like a simple metric to try to understand, is this a good cavity or a not so good cavity? So transmission peaks have a full width at half maximum, so FWHM value of delta nu C, which now needs to be calculated. And this is not really like a trivial thing to do without making many assumptions, but nevertheless, let's just like make those assumptions and be happy with it, so that we have some simple mathematical way of describing what is the finesse of our cavity. So let's first assume that the peaks have a Lorentzian line shape. So basically they are behaving in a way like ideal manner, and they correspond to the frequencies for which there is constructive interference between the various output fields. So this is basically like looking at the math, we see that that's where we have those peaks originated. And let's now calculate the full width half maximum value for this transmission coefficient. So that's basically, we assume that we want to calculate at which value the peak has been reduced to a value of 1/2. So full width at half maximum value. So that's how do we calculate the values, and then we can plug in some we can plug in the values into the transmission coefficient function, and here basically we are getting something out. So this is basically now the kind of transmission function, and we want to find out at which value we have this condition, that being 1/2. For simplicity, let's now assume normal incidence. We can finally replace everything, so basically the D term with a D cosine theta. But for now, it's just simpler to do all the calculations by just assuming that there we have a normal incidence. Right, finally, we can always generalize, but right now it's just simpler to do the math without considering the general case. So let's consider the term 4 times r divided by 1 minus r squared times sine squared of delta times phi c divided by 2 squared. Sorry, this was already squared, I mentioned. And this is basically unity. So what we get out from there is that we have this sine squared term being equal to 1 minus r squared divided by 4r. And this is approximately 0 for r values that are close to unity. And we are most of the time interested in Fabry-Pérot interferometers that are being made using high reflection coefficient mirrors. So this is a good approximation to make. And now we can tailor expand up to the first order. And what we get out is that we can write the sine squared term differently. So basically, I think we all know at this stage that the kind of Taylor expansion up to the first order is essentially just the argument of the sine squared. So that's what we get out. And now we can simplify math. We can calculate what is the delta phi c squared. So that's approximately 1 minus r squared divided by r. So that basically can be written that that's more or less plus minus of 1 minus r divided by square root of r. So basically we take out the like a square from here. So we can Taylor expand up to the first order in delta phi to get the condition that this delta phi c is basically then 2 pi times nu c divided by the free spectral range. And now we can calculate that this value of the kind of full width at half maximum is basically the kind of like plus nu c value minus the nu c minus value. So this is basically then 2 times c, and that's basically the free spectral range. And then this is basically times, free spectral range times 1 minus r divided by pi square root of r. So this is basically where we are now. So we take this, and it's a periodic function, and we are interested in calculating the full width at half maximum value. So we take the kind of plus and minus values of this so that the condition equals that we have the kind of full width at half maximum value. And then basically we Taylor expand this again to get a kind of simpler form, and then we can calculate that what is this kind of like difference in the frequencies. And this can give us then the full width at half maximum value for the Fabry-Pérot transmission peaks, and that's almost there where we want to be. So what we can do now is that we can use the above equations, and we can define an important parameter. So that's basically the finesse of the Fabry-Pérot interferometer, and that's defined as a capital F, and that's basically the free spectral range divided by the full width half maximum value of a single peak, and plugging in the values that we have, that's equal basically to a pi square root of r divided by 1 minus r. So that's basically the finesse, and this is what we calculated. That's basically the full width half maximum value of a single peak of a Fabry-Pérot interferometer, and this free spectral range is giving us the periodicity of the peaks of the Fabry-Pérot interferometer. And finesse is being defined as this kind of ratio, and using the previous calculations, we can give it this kind of simple form that basically just depends, or seems to be depending on the reflection coefficient of the mirrors, assuming that we have identical mirrors. So finesse corresponds to a Q factor for the Fabry-Pérot interferometer. So that's another kind of parameter that would tell us how sharp lines we are getting out from a cavity. So if you're more familiar with a Q factor, then you can also be kind of like using that to estimate what is the performance. And what this finesse or the cavity Q factor basically tells, it tells physically about the ability of the interferometers to store optical energy. So the higher the cavity finesse or the higher the Q factor, the more the interferometer has a potential of storing energy within the cavity mirrors. So higher the finesse, the more the more times light bounces back and forth between the mirrors, being significantly attenuated. So basically that tells us that there's more energy within the mirrors. And this is basically looking at the equation entirely dictated by the reflectivities of the input and output surfaces that basically will be acting as a high reflection mirror surfaces. So this is now what I wanted to say about the Fabry-Pérot interferometers and the main parameters of Fabry-Pérot cavities. So basically the finesse that we lastly described, then the free spectral range, so that's basically the periodicity of the subsequent peaks, and then of course about the transmission function, that's really the full function giving us the profile of transmission of light as a function of color of light going through the Fabry-Pérot interferometer. And please do remember after this lecture that these guys are used everywhere, so this is really important piece of mathematics to understand and grasp, and we will be encountering this kind of mathematics later many times in this course, so be warned that this is not just a kind of like one-hit wonder that we were describing this on this lecture. But thank you for your time and patience, and please follow me quickly to the next lecture where we'll be describing about optical resonators. So thank you, and please stay tuned.